So we are recording, and what we will look at today are some of the last concepts we have for biotechnicians in similar algebra. As mentioned, there will be a bit more for the mechanical folks later. So the heading is
Close by.
transformations.
The first thing I want to talk about is
Domain and range. What are they called in linear transformations? So let's just review something from math at level B. If I have a coordinate system here with an x-axis and a y-axis, and the graph receives some function.
If
This is referred to as the set of all permissible x values that could be input into the function. In my drawing, these would be all the x values within this range. This is called the domain of f, and it's written as dm of f. And then we talk about all the y values you can get as output, because you know that when f operates on x, which is the input, you get the output y. So the domain means the set of permissible x values. So this is the set of valid x values. And when f has acted on x, then y comes out of the system. So the set of possible y values also has a name, and you can see it on my diagram. It goes from here to here. So those are the ones located here. It's called V, M, and F, and it's called the value range. So VM, pero sí, it is the set of possible y values. And just like what I have explained here, there are some concepts that apply to linear transformations. This applies only to regular functions. Now we are looking at linear transformations, which belong to the field of linear algebra. Finished. We usually write it like this. Imagine you have a transformation f that sends you from a vector space V into a vector space W. In other words, you have something we could imagine as a function that now takes a vector as input. And what it does with the vector is that there's some transformation matrix A that you multiply with this vector, and out comes the output vector. And if we just draw it in a way that you can imagine it, I can't draw a graph like I did over here, but I can draw some sets that contain vectors. I can draw some vector spaces. So when I have such a mapping from a vector space V into another vector space W, I could at least try to draw something that one might imagine as the vector space V.
I'm just drawing a circle. It's just a set.
A whole lot of vectors live in here in our input space. That means the vectors that exist here are sent off. Is the transformation F, and then the vectors land over here in a different set, which is W. And which one was it again?
If f is yours.
If it is a linear transformation, what could we say with certainty? Well, the zero vector will be mapped to a zero vector. So if that is the zero vector in my input space, and if that is the zero vector in my output space, and note that the two zero vectors do not need to be the same dimension. For it is not certain that the vectors existing here have the same number of dimensions as the vectors existing here. So when I write a zero vector here, it could well be that this zero vector has 7 coordinates, while the one over there has 33.
You just can't quite see it because I just write a 0 with a vector line over it.
Just be aware of that, but what was the problem with such a mapping?
Well, linear. Well, then we were supposed
Over
to...
ego is transformed above into over ego. Can you remember that? It must not move. So I can kind of draw a
From
dick
here and over to saying...
I know for sure that the zero vector is mapped to the zero vector.
If it is just nearby.
This set, which contains all the vectors I can pick and use as input, is now called my domain. So it corresponds exactly over here. Over here, my domain was part of the x-axis, but now my domain is a space filled with vectors. That makes sense.
So these are definitions.
Quantity.
And the set over here, W, one might assume is the range, but it's not. It's called the codomain because it's the set at our disposal that we can land in. So W is called the range. I don't know if it's good or bad news. None of your oral questions are about this. I just need to tell you so you know. The words are space of disposition. And now comes a concept in the Highlands before, or over here in my domain. It may be that there are other vectors besides the zero vector that get mapped to the zero vector. Sometimes there are others that get mapped to the zero vector as well. The set of them is called the kernel. So imagine that there are
A set inside V. So this subset is V.
and in here exist some vectors that have the special property that if you send them off with F, they all end up in the zero vector. It is called the kernel. So this area here that I am shading is called the kernel of the mapping. And it is written KERF, and it is also called the zero space.
So it can.
It's the same as the null space. You can choose which term to use, whether you prefer to use kernel or null space. It is written like this, KER for F. And let's write down, what is it then? If we now have to write it with mathematical symbols, what is the kernel?
On my transformation F.
Well, it's a set, so I start with that. It's called a set builder. It's like a curly brace. So what kind of set is it? Well, it's the set of all vectors x which are in V. It is the set of all vectors x that lie in V, which holds true
Such
straight
a
line,
law.
corrected to the domains where it applies.
And if
Of those vectors, they are the zero vectors. Now I will read it aloud again, so you are clear about what it says. What is the kernel for a linear mapping? The set, where is the set located? Inside V, so it is a subset of V. What is inside that subset? They are some vectors. They have the property that if you send them off with F, they all end up at the zero vector. That is called the kernel of F. And I can try to illustrate that in my drawing. You should imagine that this entire area here is being sent into the zero vector.
And learn it.
And I think the reason some people came up with calling it the kernel is because you can imagine it as a figurative core surrounding the zero vector, containing all the other vectors that share the property of being mapped to the zero vector. Isn't there something called the range, like there was over here? Yes, there is. There is something called the range. I'll just illustrate that as well.
Because if you take all the vectors in V and send them off,
where can you be sure you will land then? Somewhere in W.
But it is not certain that the entire W.
You might say overwhelmed in English. It's not certain that I hit the entire W. Maybe I'll only hit part of W. Imagine that when I send all of W, all vectors that are in W, the only place it can land is here, which is a subset of the codomain. That's what it's called. Actually from the image space, and the image space is what corresponds to the word you knew as the range. So the image space is the space that contains all the images of all the vectors in V. So now I'll see if I can draw it.
that goes to the eye.
Now the drawing is getting complicated, so I have to start from the beginning.
So what is it that we just mentioned? If I have a mapping F that sends me from V into W, what does that mean? It takes vectors
We
in V.
work on them and form vectors that land in W.
If so, and how does it happen, by the way? Well, you have a transformation matrix, you multiply it with the input vector, and out comes an output vector. And note that the input vector does not need to have the same number of dimensions as the output vector. If it is a linear transformation we are dealing with, what can we be sure of? It leaves the origin unchanged. Okay? So if you visualize it geometrically, when the zero vector is sent to the zero vector, it means that we have not moved the coordinate system, including the origin. We can rotate it, stretch it, and compress it, but we do not move the origin. And therefore, the zero vector in V is sent to the zero vector in W.
So far, so good.
But when dealing with linear transformations, there can be many vectors in V that, when mapped, all end up in the zero vector. And the set of all those vectors, what is it? It is a subset of V. It is actually a subspace of the vector space V. And all the vectors in here share the same properties as those that were in V. The same properties as those that were in V are also part of the vectors that lie here in the kernel of the subspace. And so the kernel is the set of all vectors X that lie in the input space V, for which it holds true that when we send them through F, they end up at the zero vector. And finally, it's not certain that our transformation reaches all of W. Typically, it might only hit a subset of W, and what it hits is called the image space, but the entire space it could land in is available to us.
Our outline
That's
is
why
the
it's called
target
that.
outline now.
And those were just some terms you should hear and have seen. And it's not something you need to remember, but it's nice to know some of those technical terms when talking about these mappings. What was I supposed to talk about then? I've talked about that, and I've talked about that, and I've talked about that. Oh yes,
So there's something called,
dimension theorem.
and you just have to see this, because it's pretty clever.
Now
So
I need to get down on my knee here. Dimension theorem. Physicists believe in what is called conservation of energy, conservation of charge, and conservation of leptons. I don't know if you've heard of leptons, but physicists believe in conserving all sorts of quantities. And one of the quantities they truly believe in conserving is energy. A physicist, at least a physicist living today, would say that energy cannot be created and energy cannot disappear. The only thing energy can do is change state from one form to another. If the same can be said about consciousness, then it's a pretty trippy universe we live in. Imagine that the amount of consciousness is conserved. It's something to think about. I suspect so, actually. I'm not sure if it's correct. I can't prove it in any way, but you can't prove energy conservation either. But something you can prove, because now we're in mathematics, is dimension preservation. So just as physicists believe in the preservation of energy, mathematicians believe in dimension preservation. What does that mean? Do you have any questions, Lucas? The question is, you say energy conservation can't be proven, yet so far there is some evidence to the contrary, and both things are true. We don't have any examples, at least as far as I know, of energy not being conserved. Does that mean we have proven energy conservation? Absolutely not.
There are countless experiments we need to do.
And of course you can't, so you'll never be able to prove energy conservation. But the reason we strongly believe in it is that all experiments conducted so far suggest that energy conservation is true. But in mathematics, it's a bit of a different matter, because in mathematics you work with assumptions. And if you assume this, and assume that, and assume this, which we call axioms, then I can prove it. And there's really no way around it. And here comes something you can't really avoid, called the dimension theorem. And it says, if you look at the dimension count, meaning the number of dimensions in your input space, V over here. Let's say there were 13 dimensions here. So we have vectors that exist in this space, which are 13-dimensional vectors. Then the dimension theorem states that it must yield the dimension count for,
both the kernel and the image.
what does that mean? It means how many dimensions does this subspace inside V have, such that all vectors residing there are sent to the zero vector,
Plus,
plus the dimension number for the image is there. That means the image space is above. This is, of course, the image space. You can write it as f of V. That's where all the vectors end up when f has acted on them. So you pick vectors from V, let f act on them, and they land here in the image space. So the dimension theorem states the following. If you have a vector space here with 27 dimensions, and let's say that the kernel or null space is 7-dimensional, then you can be absolutely certain that the vectors ending up here are 20-dimensional. Are you following along with that? And that's the dimension theorem. And if we were doing some advanced linear algebra, you could use the dimension theorem to do all sorts of cool things. But now you've just heard about it. And it's the thing where if the determinant is 0, remember that when you solve with Gauss-Jordan, you get free variables. And the number of free variables also plays a role here. It actually indicates how many dimensions I lost during this linear mapping. Yes, that's it. That's exactly what it is, yes. So how many are there that depend solely on each other? When you don't have full rank, if you have a rank that is less than full, the rank tells you how many leading ones you can have. And where you can't have leading ones, you introduce free variables. So that's completely correct.
so that was the first board.
What else did I plan to tell you about? Oh, yes. In your case, now comes something that is exam relevant, because in one of your questions, it states that you need to demonstrate that if you have a DNA mapping, there will exist a matrix reduction for every DNA reduction where the columns indicate where the basis vectors land.
And now we will show that it is correct.
So what was it that meant having a similar depiction? Well, if I have a similar mapping, you write it like this. I have a mapping F that sends me from a vector space V into W.
And if F is otherwise equally close.
So what did that mean? What we just saw is that you can be sure that the zero vector is mapped to the zero vector. And how can you be sure of that? It's because there are two conditions that must be fulfilled if a mapping is linear.
One of them is that F
Acting on a constant alpha times some vector that lives in phi should give the same as alpha times the image of that vector.
So here I just need to write where the x vector is picked from V.
This is my input space, this is my output space. What it states here is if you pick a vector from that space,
multiply the x vector by a constant alpha.
and it can be any arbitrary real constant. So we write it like this. Then alpha just jumps out and F should just be allowed to act on X. So what it essentially states is that it doesn't matter if you first scale a vector and then send it off, or if you send it off first and then scale the result with the same factor. And the other thing that must hold is that if I now pick two vectors,
Listen up.
the vector X and X2, and then I form their sum, if you take away two vectors and add them together, what do you get?
A new vector.
These are some of the rules that apply to a vector space. Two vectors added together must also be in a vector space. So a sum of two vectors is sent. What does it give if F is linear? It gives the same result as if you sent one vector separately and saw where it lands, and then sent the other vector separately and saw where it lands, and then you add them together at the end. you should get the same result. These are two quite nice properties that must be satisfied for a mapping to be linear. And then your minds might wonder, what does that mean? Geometrically, it simply means that all our grid lines, which were parallel to start with, they remain parallel after the transformation. And there was an equal distance between all our grid lines before the transformation. There is also after the transformation. And one could say it in another way.
Numbers are being multiplied and added together.
Then a mapping is linear. But if a mathematician were to say it, they would write this. They would say, if the image is a scaled vector, gives the image of the vector itself multiplied by the same scaling constant as before, then you have one of the criteria for the linearity. And if the sum of two vectors sent becomes the sum of the images of the two vectors sent separately, then it is linear. So both things must be true, and they are usually combined into a single condition, which I've shown you, and it looks like this. Let f act on a linear combination of two vectors like this.
So it says
Sends
here,
off a linear combination of two vectors from V, and if it results in the same linear combination, but just of the images of the vectors. So notice that I am using the same two constants, alpha and beta, again here. That's what I mean by the same linear combination, but now it's the images I need to make the linear combination of. Then it is linear. So this is requirement 1 and 2 combined into one requirement. I could just put the box around it. And from this, it immediately follows that the zero vector is always mapped to the zero vector. I can actually prove that using the one mentioned up here.
So one can claim something.
One can assert something in a mathematical sentence, which is that the image of the zero vector always becomes the zero vector if the mapping is linear. And you can prove that very easy just by looking.
This rule should not be followed.
Then option 1 is waves.
What follows then? Oh yes, what does f give when acting on a zero vector? Well, I should maybe mention again, you cannot be sure that this zero vector has the same dimension as that one, because that one exists in V, but that one exists over in the codomain W. So that one could be, in principle, a two-dimensional zero vector being mapped to a 27-dimensional zero vector. We have no other way to write the zero vector than 0 with an underscore if we want to write it concisely. Otherwise, I would have to write it like this.
0, 0, 0, and then I need to write 27 zeros.
So it is implied that it is not certain that we mean the same thing by the zero vector symbol. We just mean some vector where all coordinates are 0. And how can we then prove that it is true that f of the zero vector always gives the zero vector? Well, you can do that by looking up here, because how can you write a zero vector in a clever way? From V, well, I can just write it as the number 0 times any vector from V. No matter which x I take from V, if I multiply it by 0,
Then all the coordinates become 0.
and what happens with that 0? Alpha jumps out in front. So 0 jumps out in front here. And now you can see, regardless of what vector this gives, when you send x through f, if you multiply it by 0, it definitely becomes the 0 vector. And now we have proven that a similar mapping sends the 0 vector to a 0 vector. And now comes another sentence that I would really like to prove. If you have a similar mapping, meaning one that adheres to this and that means one that only adheres to this, then it follows that there exists a mapping matrix that does what it should, where the columns in the mapping matrix just are where the basis vectors land. I would like to prove that. So that is my theorem, what I just said there. So here comes a theorem that says let f be a linear function that sends a vector from V to W.
there exists.
Yes.
A mapping matrix.
Listen now.
To F, that is to the linear transformation with columns.
With columns that tell a story.
For the basis vectors.
Basis vectors.
I don't want to.
Send there. That's what we need to prove.
Let me just say it in Danish. If you have a similar illustration,
Then we claim that you can always express it using a transformation matrix that simply multiplies the input vector. And what I am claiming is that this transformation matrix is very easy to find. We just need to examine where the mapping sends the unit vectors, the basis unit vectors from V, then you write them as columns, and then you have the transformation matrix. We have used this a few times, but now we need to prove it. So let's prove it. And the first thing I can prove is that the marker I'm writing with is close to being useless.
but I think I'll try to get through with it during a break.
Good
We
evening.
forgot to take some fresh ones down and just grab some. So
Imagine that you
V is one-dimensional.
our input space, which is n-dimensional, and imagine that W is m-dimensional. Okay, so there aren't the same number of dimensions. They don't really need to be. If V is n-dimensional, what does a vector look like if I pick it from V? Now I pick a weightage in, and I call it x. If it is n-dimensional, how many coordinates does it have? N. If it's 10-dimensional, it has 10. If it's 27-dimensional, it has 27. But now it's n-dimensional, so it has n. So it has a first coordinate, a second
And
coordinate,
all the way down to the final coordinate.
and what does a coordinate column mean again? Let's review that. Do you remember? It means how many pieces do you have of the first basis unit vector, plus how many pieces do you have of the next basis unit vector. So when you write a coordinate column, you always refer to a basis. And let's say that a basis for V has n basic vectors, and they are unit length and mutually orthogonal. So it is an orthonormal basis for V, and it is here. I call it E, and it contains all the basic vectors from the vector space V. That means here is the first unit vector.
Here is the next unit vector.
And now they are not called I, J, and K because there are too many. So there aren't enough alphabet letters. So they just call them E1, E2, and so on up to the last one I need, which must be En. And why do I need N? Well, because V is n-dimensional. So there is a unit vector that spans the vector space V. And maybe you remember when I write a vector like this in high school, 2/3. What did that mean again? It meant take 2 of the unit vector I plus 3 of the unit vector J. That's what it means. So what does it mean when I write vector X now with these coordinates? It means take so many of this unit vector plus take so many of that unit vector and so on. Take so many of this unit vector. Are you following? That's what it means. So therefore, I can write my vector X like this as X sub 1 times the first basis unit vector plus X sub 2 from my coordinate column times the second unit basis vector. And I just continue like this until I've gone through all the coordinates to the last dxn times a vector. I have written quite a lot, but I haven't said much. What have I actually said? I have picked a vector from V, and V is n-dimensional. Now I send it off with F. So I really want this sentence here.
Beast,
So I have to try to send it off with f and see what happens. So let f send.
X vector is the place.
That must mean I should take this whole chunk, which is the x vector, and plug it into x's place. So it results in f acting on all of it. This is quite a bit of writing work here. There you go. Now I am about to send off my vector. But I know it is linear because I assumed that. Because my statement was about what I can say if it is linear. So that applies. So what it says there. If you let f act on a linear combination of vectors, it gives the very same linear combination of the images of the vectors. So I'm using that now. So what does f give of this? Well, it gives x1, which was the first constant, times the image of the first unit basis vector, plus x2 times the image of the next one here. Unit weight goes up, plus so on.
X inches. The scene is the final unit vector. And
that there, what have we seen before? That is a matrix vector product written in disguise. A number times a vector plus a number times a vector plus a number times a vector. How can you write that? You can write it like this. You just create a matrix where the first column is that one.
That's not a number one. It's to show that this indicates the first height.
Okay. And just notice, how many numbers should there be in this row? How many are there down here? There must be M and over there in the output room. So when F has acted on a vector, where does it land? Over in W. And how many dimensions did W have? M. So there are M numbers in that column. And then the next column should be the next image of the next unit vector. And we continue this way to the last one.
All of that becomes a matrix, which if I multiply it by this
Vector
one,
provides exactly what is written.
Sit standing.
And here it should say x1.
x2 dot 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 down to xn, like in Norway. And then it is
Thank you
PV.
for watching.
Yeah, here it is. This is your mapping matrix. And what does it contain? Columns. Which columns? The columns that show where the basis vectors land under the transformation.
So what does it say here?
There are m rows
And one pillar, so it is a
Times a transformation matrix.
and this might seem a bit intimidating the first time you see it, because you might wonder, why would I ever write this down?
but there's really no difficult math in it. You just need to keep
On
track of it, what is being said. So it is much more about
Calm
language really,
exercise.
rather than heavy mathematics.
So in a moment when you are done taking notes, then I'll point it out and go through it again. Then we'll pause the recording.
And go out and train.
This is basically the last linear algebra for the biotech students. Then we are through with our linear algebra.
Then there was a bit about the self-esteem issue for the engineers.
a little later.
and we're doing that
The
now.
others are finished. So what are we saying here? In mathematics, if someone has come up with something called a linear transformation, what can it do? It can take vectors, do something to them, and generate some other vectors. And vectors are very general in mathematics. You can have polynomials of degree at most 2, which are vectors, where all the coefficients of the polynomial form the vector. So this is something very general we have learned here, which can be used in many places in mathematics. Unfortunately, we don't really get to discover it in Mathematics 1. There is a transformation called the linear if it behaves quite nicely. And these are the two things it does. It sends a constant times a vector over to the same constant times the image of the vector. It does that if it is linear. And it does something more if it is linear. It sends a sum of vectors to a sum of the images of the corresponding vectors. And these two conditions can be written as one. If a transformation behaves like this, then it is linear. What does that mean? Explained with images. Origin stays in the same place, and the grid lines remain parallel and equidistant, meaning an equal distance between them. It can be proven that the zero vector is always mapped to the zero vector. We did it like this. We simply stated that the zero vector can be written as the number 0 times any arbitrary vector. And due to that property mentioned above, the 0 comes out front. And the image of any arbitrary vector gives an arbitrary vector. But when multiplied by 0, it will always result in the 0 vector. And note that the 0 vector and the 0 vector do not need to have the same number of dimensions. Like claim, if F is a linear mapping that sends us from a vector space V to a W, then there always exists a mapping matrix that does the right thing. And you create it by simply writing columns into the matrix that indicate where the basis vectors land during the transformation. It is incredibly important to understand this because it allows you to create a linear transformation that does exactly what you want. You just start by thinking, what do I want to happen to the space? It should be stretched by a factor of 2 in that direction and by a factor of 3 in the other, for instance. Then you simply look at where the unit vectors land, and when you do that, you have your transformation matrix. This is what we are proving now, and that is why this is important. It helps you understand how to create linear transformations that do exactly what you want them to do.
And to
So
become
let's imagine in general that V is an n-dimensional input space and W is an m-dimensional output space. Now pick a vector from V. How many coordinates does it have? N. Why? Because there are n. There were n dimensions in V. How many vectors are needed to span V? Exactly n are needed. Yeah? You cannot span the 10-dimensional space with fewer than 10 linearly independent vectors. Moreover, you cannot have 11 linearly independent vectors in the 10-dimensional space because one of them can be written as a linear combination of the others. So it requires exactly n linearly independent vectors to span an n-dimensional space. Because if you have fewer than n, you cannot span it. And it is not possible to have more than n, as then they are not linearly independent. Okay, remember to talk to me about last time. Here is an input vector. Now send it through F. That's what I'm doing here. Take advantage now of the fact that F is linear, so that there is the same as that. By using this rule stated here, I recognize that as the result of multiplying that matrix by that vector. Then we are done. And perhaps it's exactly from here that you can't see it. So after the break, I'll show an example where you can see how to go from there to metal. And that's when I was just staring the first time I saw it. Yeah, let's take 10 minutes. And if you want to post the recording, we'll meet again after the break. It was a black marker. Yes, let's just get a black marker. We hope to have a good break. And let's now take a look at the result. And then let me explain it, where I was puzzled the first time I saw this derivation. What you need to realize is that when F has acted on a vector, what comes out? Also a vector. So what is written here is actually a vector. And if the contents have n, as in no dimensions, how many does the entire vector here have after F has acted on it? Well, when F has acted on it, we end up in W, which is m-dimensional. That means this vector has m dimensions, meaning m numbers in its coordinate column, as shown here. So here are 1, 2, 3, 4, 5. You are an m number in the first column. So this is a matrix with m rows. And the number of columns where there was a unit vector that needed to be sent off. So there's one column. The next thing I was puzzled over is why what's up there can even be written as what's down there. And it becomes easy to see if you just take a pencil and do it.
Let's just see how I got from here.
And here too. So we could imagine that we are looking of an example. Let's say we have a mapping F that takes us from the 2-dimensional space into the 3-dimensional vector space.
that means you can see there is dimension data over here.
Greater than here. So the one that plays the role of being my vector space V and the one that plays the role of being W. And now I can come up with that F of X vector.
Now I can
So
go
draw
over
the vector line.
because the input
It
weight
lasted for 2
is
hours.
working.
We can just write it down. My X vector looks like this. It has 2 coordinates, x1 and x2. And what does that mean again? It means to take x1 and multiply it by unit vector I and take x2.
And multiply it by unit vector j.
So when f has acted on the x vector, a y vector emerges. The y vector, I can also put a vector arrow over it because it exists in 3 dimensions. So it's also a geometric vector that can be
Good
illustrated.
evening.
So my y vector has 3 coordinates, y1, y2, y3. Since it is a 3-dimensional vector, a set of course means y1 times unit vector I plus y2 times unit vector I.
Unit vector j plus 3 times unit vector k.
And now let's just invent this one.
Line of transformation. Now I'm composing. I'm making it up.
I say, okay, I need
3 rows, right? Because I want to end up in R3, so I need a 3-dimensional vector as output. So what's going to happen here? Well, the only thing that needs to happen here is something that multiplies and adds numbers together. On what? On the input vector's first coordinate and second coordinate. See? The input vector has x1 and x2 as coordinates. So if I say, for example, 3x1 plus 2x2, out of that comes a number, and I can use that number as y1 as the first coordinate for the output vector. Then I need another one here that can be minus x1 minus 5 times x2.
And finally, 4 exits.
Minus 2x2.
So this is an example of a similar department.
And
How can we write this? This has to be equal.
Your 1 over your 2 over your 3.
Well, we can write that as 3 equations.
1, 2, 3 equations. Can you see it?
And how many unknowns? 2 unknowns.
So that means it will say something like this. 3 times x1 plus 2 times x2.
Alone with the y.
And minus x1 minus 5x2 must be equal to y2.
List 4 by 1 minus 2x2 should be equal to y3.
And here we can read our coefficient matrix. Okay. Our coefficient matrix is exactly the same as our binding matrix. It will then be called 3, 2, 3, 2, minus 1, and minus 5.
And 4 and minus 2.
You see that there are 2 columns and 3 rows. And if I took this vector, x vector, which had the coordinates x1 over x2, is it then possible to multiply that matrix by the vector? Well, yes, it certainly is. Look, if I take my A matrix and multiply it by my x vector, then I get this matrix as we just wrote earlier.
And now I will try to multiply it by this one.
Exits.
Extra drawing.
And then we had to say this times this plus this times this. And this times this plus this times this. And this times this plus this times this.
And if we do that, we get 3 times 1 plus 2 times 2. That's what it said there. And if I take that row 1 column, I get negative x1 minus 5x2. That's what it said there.
And the time that plus the
It
time
is
that
4 times 1 minus 2 x2. That's what it said there.
So you can see that you can move from a structure that looks like this to a structure that looks like this.
And now we have shown that the mapping. Turn on each division nearby. There is a department matrix.
Yes, Nikolai? Yes, it does. Because this vector here is m-dimensional. Because when f has acted on the unit vector e1, it lands over in W, which I assumed was
It's
m.
me who is necessary.
We only go up to n in this direction.
there are n columns, but there are m rows. So that means try to look over here. How many rows do you have here? 3. How many columns? How many columns do you have in this one? 2. And that corresponds to transitioning from 2 dimensions to 3 dimensions. So the number of columns corresponds to n over here.
The number of rows is equal to m.
Does it make sense when you see it now? So if there are 3 dimensions over here, then there should be 3 rows. Is that right? Yes, there were 3 dimensions here, and there were 3 rows. These lines indicate that the day you know the image of E1, you should write the entire coordinate column here. And how many numbers are there? M. And we need to have m rows. So here it was implied that the image is a unit vector. This one, it gets a dimension number and m. This is how we write it. The dimension of the image is the same vector E1 of m. And this also applies to all the others. And that's why you get m rows and n columns. And you can see in my example that it doesn't match because I went from R2 into R3. So you should expect beforehand that there are 3 rows and 2 columns. And that is also the case in your binding matrix. I think we should go out and train and present this story. So let's pair up 2 by 2 and go out and find some boards and practice it. And I will go around and help. So if you'll pause the recording. We have been out training. The next thing we will do is start on a completely new topic. And if you are part of the machinery group, then we will revisit your algebra once the biotech curriculum is complete. So what we will cover now are first order differential equations. So that's the headline. Differential equations. First order. And later, we will then have the second order frontal mappings. The question that might arise in the mind of someone reading that headline could be, what is a frontal adjustment? So let's just assume that you know nothing about this topic. Then I'll start by telling you, what is a differential? And that is what I assume you know nothing about this topic, because you might not remember it.
And to save the differential line vanished.
Yes, so I'll start by clarifying what it is not. Here comes an example of something that is not a differential
But
line.
an algebraic equation.
And an algebraic equation. This is the kind where what you are searching for is a number. So it could be like this one. 2x should equal 8. This is actually an example of a linear equation with an unknown in the topic we just covered. Yeah, and if you are to find x here, you need to find a number that when multiplied by 2 gives 8. And there's only one number with that property, which is the number 4. And now you say you have solved the equation, and you write a by implication arrow in between. And what's actually happened is that we've divided by the number 2 on both sides of the equation sign, and then we get the solution x equals 4. That is not a differential. It is a linear equation.
What is
a differential equation? Well, it's an equation where what you're looking for is the derivative. What you are looking for is a function instead. So it is a bit more complicated. And let's try to give an example of a differential equation. It might be that someone asked, can you find me a function? If you differentiate it, it gives 2. It is a question of gaining understanding. What is implicitly written here, which you can really see unless you're used to mathematics, is can you find all functions that, if you differentiate them with respect to x, give 2? That's what it says. And then you can start to think about what it means to find a function that differentiates to give 2. It means you need to find all functions where at every point on the curve on the graph, the slope is 2. Because to differentiate means to find the slope. Remember? And what are the functions where at every point on the graph, the slope is 2? Where those are all the straight lines that have a slope condition of 2.
So there is a whole range of solutions to this problem.
Here is one solution.
This is the y2x function.
Because the function y equals 2x has a slope of 2, no matter where we are. And what does that mean? It means that if you stand at a point on the graph and take a step of 1 to the right, you need to go up 2 to hit the line again. Then the slope is 2. But is this the only one?
It is function.
There is a slope of 2 everywhere. No, that's not right. All straight lines.
It is called 2x plus b, where b is wildly.
Call it constant. All the straight lines are functions with a slope. So therefore, if one is to solve this, one can provide a single solution, which is called a particular solution with 2x. A particular, and it comes from the English word particular, meaning a very specific, very definite solution. Solution could be
Rune.
B. Are they with 2x?
But it's not the
There are
only
infinitely
ways.
many solutions, namely all the straight lines that have a slope of 2.
That's what I need.
That is called the complete solution, if you include all of them.
So the complete solution is
The complete solution is that y equals 2x plus some random constant. Now you could call it b, or you could call it k. We usually call it k or c for constant. In English, constant is with c, and in Danish, it's with k. So people tend to write k. So k here can be any arbitrary real constant. And that's called the general solution to that differential equation.
Whereas that there,
It is a particular solution that adheres to the condition that it fits the monicon.
so it is a quite specific solution.
Let's try another example, so we can start to discover what differentiations exist. Example 2.
it could be that we have a differential called the y mark. It must equal y.
What's that now written there?
What it says in mathematical terms is catalogic differentiation in strange y. What's written in Danish is, can you find all functions that, if you differentiate them with respect to x, they yield themselves? And it requires that one remembers all the differentiation rules to think of it. But I can think of a particular solution. Particular. So a specific one could be that y is x. Y is a function of x here, implicitly, right? That's called a to the x, because what the exponentials give, when you differentiate them, it gives itself. The exponential function solves the differentiation, so that is one solution. How do all the solutions look then?
What does the complete solution look like?
Well, the complete solution looks like this. Y of x equals a completely arbitrary constant, c times e to the x. Why? Well, because what do you get if you differentiate this? A constant times a to the x. What does that give if you differentiate it? If you have 7 times a to the x differentiated, well, 7 is a constant that's multiplied. And we've learned that it remains unchanged when you differentiate.
So the 7 ex's become the 7 ex's.
Yeah, is it then true that this satisfies that equation? Yes, try to differentiate it. What does ca to the x differentiate to? It gives ca to the x. Then insert it there and check if it equals y, where you just copy paste y. Well, it does. And notice one thing. What I'm saying now is important. If something is to be a solution to a differential equation, it must make the equation true for every value of x. Yeah, so that's a completely different story. Over here, the equal sign should be true, but not for every value of x, only for the value of x where x is 4. So the equality sign in a differential equation is much more demanding. It has to be valid for all x values. It must be eternally true. And as a physicist, you would think it has to be true at all times. So Newton's second law.
That's a differential equation.
And we believe in it, not just on Sundays.
Is it okay to look? Maybe not.
We believe in it all the time. And therefore, Newton's second law must be satisfied for every value of t. This is a differential equation. And this is a differential equation where the independent variable is called x. So it must hold true for every value of x. And it is said that the differential equation is satisfied if y of x is equal to that. We can quickly demonstrate this by performing a verification calculation.
And to perform a check calculation, I first calculate the left side of the differential equation.
So I calculate the right side. This is easy. And then I see if they are equal for every value of x. So what does the left side give? The left side was y prime. So I find it by differentiating. So I just differentiate this. C remains the same. And e to the power of x is straightforward. So that's sorted. Now I've calculated the left side. You can see that this is a basic example I'm starting with, but it's to get a grasp on all the fundamentals. Then I calculate the right side. Well, it was just y on the right side. So it naturally gives just what I proposed it to be. And now we can see that since the left side equals the right side, that is indeed equal to that. Regardless of which x we choose, the equality holds. So that is the complete solution. It is a solution we have shown. We haven't actually shown that it is the complete one, but it is. There are no others. Or maybe there could be someone in the class who says, what about 0? The function called y equals 0. Doesn't that work? It is simply a horizontal graph that looks like this. If you differentiate 0, what do you get? Is it true that 0 is the same as 0 for any value of x? Yes. So y equals 0 is also a solution. This is called the trivial zero solution. So this is a solution. And it is called the trivial zero solution. For it doesn't have any physical interest. It's not the physicist I'm interested in. If they're modeling how many people are on Earth and they conclude there's 0, then it's great that it solves their differential equation. But it's quite uninteresting. Yes, the differential equation holds true if there are no people in that area. So that is a solution. And it is called
The trivial null loop.
we've got this.
0 to 2.
Good evening.
Well, y equals 0. I've already written that down here, right? I could have just said that c was 0. So typically one would write it like this. That c can just be any real number.
Or you will see
Then
0
you
will
get
also
0.
be included as the solution.
So this is actually not a new solution. It was one I had already written here.
If you think about it, it came up if you let C be 0.
That was me. You can create a differential equation that has no solution, where you impose certain conditions.
Modeled.
And you can
The
easily
differential
make
you can't figure out how to solve.
And there are far more that we cannot figure out how to solve than those we can. And unfortunately, there are also some of them in the universe around us that we cannot solve. For example, wave equations and pulse equations. They are differential equations. And we can mostly solve them because they
It
are
was a
simple.
situation where I am looking at hydrogen atoms.
But there is a whole class of differential equations we can solve. And those are the ones we will learn about. In this course, we will learn about first-order differential equations that can be solved. And this is a particularly simple class called linear differential equations, because they follow the same structure as in linear algebra. And we can solve those.
And if we can't do it by hand, we can usually do it with a computer.
And if we also have to give up using computers, sometimes you can create numerical solutions that just demonstrate the solution
And some
strength.
symbolic expression for it. But we can usually get away with that as engineers.
So let's try taking another example.
Example. Let's say we have a differential that is called y prime plus 2 times y equals 3. Wow, it already starts to look more difficult. Can you see it? We are looking for a function. Because when solving differential equations, what do you find? It's not numbers, it's function. So we're looking for a function, and it is not a function that depends on x, that's implied. So we are looking for a function y, which depends on x, like that.
That if you differentiate it with respect to x,
and then multiply the function by the number 2, and leave it unchanged, then add, it should give the number 3 for any value of x. And you can already see now that it's quite hard to grasp that in your head. Up here, we could guess it, and here we could guess it. But even here, it's almost impossible to guess. What is this function? That if you differentiate it and add it with 2 times the untouched function, it gives the number 3, no matter what x value you choose. I know it because I was the one who decided to record us. And because I once learned how to solve these differential equations that look like this, I know exactly which formula to apply, and I can do it in my head. So I can pretend like I figured it out, but I actually couldn't. But now I'll write down the solutions and show that it's a solution. So here's the solution. I of x should be 3 divided by 2 plus an arbitrary constant times e to the power of negative 2x. That is the complete solution. And I will just show you that there. And later we will discover what I did to write it down. So this
is the complete solution. Could we also have come up with a particular solution? Is that where we are actually going?
I could have provided a very specific one. These are all the solutions that exist, but there is also a particular one. Maybe you can figure it out with me right away. What about the screw when I chose that one? It was just big 3.5.
I equals 3.5.
It's a
Is
function.
it even?
Yes, it is. It's a function where no matter what x you give it, it outputs the y value 3.5. So it looks like this and goes through 1.5 up on the y-axis. Are you with me on that? Does the function that is just called 3.5 work? Let's just examine it. If the function is called 3.5 like this, what do you get when you differentiate it? What does a constant differentiated on its own yield? 0? Yes. So y prime is 0.
Let's try inserting it. I am putting 0 in that place.
Plus 2 times y. What is 2 times 3 halves?
Yes, that makes 3. So now it says 0 plus 3. Is that true? Is it equal to 3?
And if it is true for any value of x, then that is indeed a solution. It was just a very boring solution, but it was a solution. Now I will just erase the left side of the board, and then I will prove that this is also a solution, even though that term is there. That was it. No, it is a new example. This is the example. 3, when asked, should it satisfy that e equals y? It should not. It must satisfy that e plus 2 times e equals 3. This is a new example called example 3. So in example 3, it says, can you find me a function that if you differentiate it and take it untouched and multiply by 2 and add it, you should always get the number 3, no matter which x you choose. And I claim that this is the complete solution. And I claim that that is a particular solution. And you realize that by trying to differentiate it, where 3 halves differentiated gives 0. So now I put 0 in that place. Then I say 2 times what y was, but I suggested y should be 3 halves. And 2 times 3 halves gives 3. So now we ask, is it true that 3 equals 3 for any value of x? Yes. So this is a solution. And this is a
particular solution.
And now I would like to clarify that it actually is a solution, because that's something I've just claimed. Just so you're clear, what does it mean to have the solution to a differential equation?
I can't remember which part I got up to, so it's part 1, which now turns into board 2.
So Hello there. I will just clarify that what I have written here is a solution. So my differential equation was called, and I'm still working on example 3. So continuing with example 3 here. Continue. And in example 3, it states that you need to find a function such that if you differentiate it with respect to x and add that to 2 times the unchanged function, it will always equal 3 for any value of x. And I claimed that this would work. So how do I verify that it's correct? Yes, I first calculate the left side of my differential equation. It gives, and then I test if it matches the right side. I don't need to calculate the right side because it's stated to be 3. So all it requires is for me to calculate the left side and see if it equals 3. Let's calculate the left side. What does y prime plus 2xy yield?
I think we'll share.
So we need to differentiate this down here. So you can see that you need to be good at differentiating to understand differential equations. Yeah, what does a constant standing alone differentiated give? 0. What does a constant multiplied by a function differentiated give? It yields the constant, remain. So C survives because it's a constant being multiplied. It stays when we differentiate. You probably remember that from our differentiation rules. And e to something differentiated gives e to that same something as before. Remember? But it is a composite function. So you need to use the chain rule.
And it will repeat rules for calculation from about a month ago or something like that.
What does differentiating e to the power of minus 2x give? It gives e to the power of minus 2x. If you remember to multiply by the derivative of minus 2x, and that gives minus 2. Can you remember that?
Because negative 2x differentiated gives negative 2.
So now I've found the y mark. So I just need
That's
to
plus
say
2xy. So I'll do that. Plus 2xy. But y is right here. This was my guess for y. So note that there are 2 terms. Thus, it should say 3/2 plus ce to the power of minus 2x here. So I'll just simplify it a bit and see if it gives me something neat. And if it gives the number 3, then I'm really happy because then it matched the right side. See, this was the left side. I calculate, check, calculate the left side and see what it gives. And if it matches the right side for any value of x, then it was a solution. So we try to calculate this. I can write this as minus 2, CA minus 2x, because the order of the factors doesn't matter. So I just move the number minus 2 to the front. And here I multiply 2 into the parentheses. I multiply it with this and with that. And when you multiply 2 on the fraction, you need to multiply the numerator. So 2 cancels out. So it's just the number 3 that remains. And when I then multiply 2 into the second term, it becomes plus 2 times CEI minus 2x. But now the magic happens. It's about to cancel out because I equals its opposite.
So the only thing left is the number 3.
Is it true that 3 equals question mark? Does it equal the right side? Yes, it is. Where does 3 go? Well, what have I now proven? That is a solution. So again, what is a solution to a differential equation? It is a function that, if you insert it into the differential equation, makes the equal sign true for any value of x. That is the differential equation I have. And it took me a long time to grasp that. I hadn't understood it when I graduated from high school. I had solved them, but I didn't understand what I was doing at all. And I remember when I discovered what I was doing, it was in mechanics. In the first semester of engineering studies, my teacher said that a differential equation must hold true at every point in time. Then I realized that these are functions we're discovering. That constantly makes the equation true. For example, Newton's second law, force equals mass times acceleration. That is a second order differential equation. And if something complies with that, what does it do? It oscillates. If you have a spring and you have a mass in it and you pull it out, then the spring gets stretched and then you release the mass. So you stand like this and it swings back and forth. And throughout that story, there is strong mass times acceleration abstraction. Okay, when the spring is at its unextended point, what is the force from the spring on the mass? 0. Does the mass accelerate then? No. But it can move, but it doesn't accelerate. Then it compresses the spring, and the force on the mass grows now. So Newton says that force equals mass times acceleration. So you need to start accelerating. Dear mass.
Brake. To brake is to accelerate.
It's just a negative acceleration. Then it slows down completely and stands still. And now the force is maximum from the spring, because the spring is fully compressed. So now it accelerates to the maximum, but it remains still. It can actually accelerate maximally, but still be stationary. Just like when you floor the accelerator in a Tesla, you accelerate maximally, but it remains stationary. And then it picks up speed again. At some point, the spring is fully extended, and now it moves at a constant speed. Now it does not accelerate. And then it stretches the spring, and now the spring force changes direction and slows it down again. And then you have something that looks like this. And to describe that motion, you have to solve a second order differential equation. And that is Newton's second law. This means you need to find a function that satisfies the equation at all times. And that is a cosine function. And that's why the graph looks like this. And it swings like this. And the same goes for a pendulum. It is also a law of oscillation. So that was when I realized what a differential equation is. That's what I used in physics. A differential equation is an equation where what we are looking for is a function that satisfies the equation for every value of the independent variable. And it can be time, or it can be position, depending on what kind of differential equation it is.
Yes, Michael. For example, it could be
a circuit where you have a resistor, a capacitor, and a voltage source. And then you are interested in finding out how quickly you charge a capacitor. It could also be that you make a cup of coffee and fill it up from the coffee machine, and it is perhaps 82 degrees hot. Then you set it down and forget about it, and now the temperature drops, and it approaches the ambient temperature asymptotically. This is known as Newton's law of cooling. It is a first-order differential equation. And if you've solved it, then you can say that if I forget the coffee for 12 minutes, it'll be 27 degrees warm when I pick it up. You can calculate that completely. We can conduct the experiment and show that it fits. So differential equations, what can they be used for? It is easier to answer what they cannot be used for, because there is almost nothing. Differential equations are everywhere around us if we try to apply mathematics to the world. When I speak, if I produce time-varying pressure waves in the air, they make your eardrum vibrate, creating electrical signals that go to the brain and are interpreted as sound. When you see the color green, is it because there is something green out in the universe? No, it doesn't actually exist when there is green. What happens is that light, which is a coupling between an electric and a magnetic field, propagates through space, hits your eyes in the photosensitive cells on your retina, produces an electrical signal that is interpreted as green.
That's how naive he seemed. It's not anything real.
And we don't even know if different creatures perceive green the same way, but our language agrees that something is green.
It can get quite strange to think about. We have no idea what is really out there. What is reality?
The only thing we know is when we measure something specific, we get something specific from measurement. But what reality is, that is an open question. Differential equations can be used to mathematically describe what we measure. It could be the temperature arriving,
Kraft,
or how quickly the charger
which
arrives.
starts up in an electrical circuit.
Table 3. What comes next is important because it is directly relevant to your exam.
So it's
For
certain.
the importance of all the other reasons too.
It is in regard
But
to
it is
an
also
exam.
important.
Someone decided that we should hold.
It is about being able to solve a whole series of differential equations that appear in a certain way. And they look like this. The heading is now first order linear differential equations with variable coefficients. That is a subheading for that one. So then first order line echo. And there's a really good reason why it is called linear. It's because it has the same structures as in linear algebra. So we'll look at that at some point. The first order linear differential equation variable coefficients
That was quite a headline. What does such a bandit look like if it's first order? With variable coefficients. Okay? It looks like this. A function you don't know. Differentiated. Plus a feature you already know well. That depends on x, which is multiplied by it, without differentiating it. It should give another function that you also know. I don't know if you can imagine how difficult it is to answer that question in general terms. But otherwise, I can read it out loud for you once more. You need to find a function that depends on x, so that if you differentiate it with respect to x and take it unchanged and multiply by a known function of x, then it should yield another known function of x. That's quite a question. And of course, it's not just to torture the students that we need to solve that differentiation. It's because it appears all over the place in physics, that specific type. And it turns out that you can actually solve this particular type by manipulating the equation until the solution crystallizes. And the formula that emerges from it is called the armor formula. We call it that because it looks quite imposing and armor-like. But now you will see how to go from the problem to the solution. So this is the task. And you will see me do it a couple of times. So don't be afraid if you can't remember everything the first time. This is the task. We need to solve that problem. This is our problem. Now I will show you how to arrive at the solution. To arrive at the solution, a clever mathematician came up with something ingenious. And we just say it's clever, and then we learn it. So it wasn't me who came up with it, nor anyone I know figured it out. Not a single one of the smart ones from D2 thought of this. Someone came up with it, and everyone else repeats it. It's probably Newton, or Gauss, or Euler. One of those annoyingly clever guys. But someone thought it was clever to multiply the differential equation by this.
Let's get started.
Euler's number raised to an antiderivative of f. And then you might be sitting there thinking, oh, I did that. Where did that idea come from? The story doesn't say anything about that. It's just good like that. See what happens? See what happens? And that's the point. When you're at an oral exam, you just say, now I multiply by e to the f, because it has proven to be a good idea. And the examiner is completely baffled. And so am I, because none of us know who came up with it. We can see that it was a good idea, just like you will soon. You don't need to understand it more deeply, because
I also want to start getting something
someone else discovered it
for blanks.
So we just learn to repeat it. So we multiply by e to the power of capital F on all parts, because it has proven to be smart.
And let me just repeat for you. Who are we leading?
Who do we know? We're looking for y.
And we know f, and we know g. So it's not f you need to find, and it's not g you need to find. Those are given in this problem. What you need to find is a function that is differentiated plus left untouched multiplied by f, I, and g. That's what you need to find. And now we will do it. We multiply by EF, and f is an antiderivative of f. What does that mean again? It means that if you differentiate f, you get f. Do you remember that? Now I will do it. Then it will say EF.
Gange. What is that?
That's what I get in the first term when I multiply by EF there. Plus, multiply by f here. So where are you standing here? And then, of course, I also need to go to the right side and work with E in capital F. So it says E in capital F. Multiply I. And now comes something clever. And you can easily think it's smart when you've practiced, because then you can see it right away. But if you haven't practiced, it's not always so hard or not so easy, but it's not so easy to see what I see now. So let me just tell you how I saw it. The whole left side here, all of this can be written much nicer. It can be written like this.
And now I will explain why it can.
And this is exactly where you get caught in a trap if you don't have it under control. So make sure to understand what I'm saying now. And if you don't understand it, come and pull me aside until you do, or interrupt, or shout out,
or something like that. Inside here, this is the product. And what does ddx mean? It means that now I'm differentiating. How do you differentiate a product again? Now let's go back in time more than a month to when we repeated calculus. You differentiate the first factor multiplied by the second factor, unchanged, plus the reverse. First factor unchanged times the second factor differentiated. Do you remember that? So let's try to do it. What does E of capital F give if I differentiate it? Well, E in capital F, that's obvious. So it gives E in capital F. But remember, it's a composite function. So you need to differentiate capital F. And what does capital F differentiated give you?
Little f. So take a look. The first factor differentiated is straightforward.
If you remember to multiply by the inner function differentiated, which provides the slower. So what have I written here? Is the first factor differentiated? It should now be multiplied by the second factor untouched. So I multiply by y. And then the product rule says Roman calculation rule number 3. If you remember it, then write a plus and do the opposite. Take the first factor untouched, e to the capital F, and then multiply by the second factor. Differentiated.
It's on brand, you know? Are you with me?
That's how you differentiate that product, because the first factor is a composite function. So you need to use Roman rule number 5 from our calculation rules. So you actually use calculation rule 5 within calculation rule 3, where rule 3 is the product rule and rule 5 is the chain rule. Try to see what is written here.
That's an exact copy paste of my left side down here. Can you see it?
Can you see that the term here matches exactly the term there? And the term here, if what, is there if what?
So yeah,
I have now thoroughly argued that I want to rewrite the entire left side to that. So I'll do that. So what do we have? We have that if you differentiate with respect to x,
and raised in great F times y.
so it gives the same result as what I already had here. So I can replace what I had with what's over on the right side. I haven't done anything there. So I just copy paste and it says E in capital F.
Times g of x.
And there might be someone in the class wondering, why did you do that? What did you get out of it? And something really clever has come out of it. Everyone take a look up here now. I also had to solve this differential equation. That was my problem. Where are there ways in this equation? There are ways both here and there. And not only that, here it is differentiated. How fun is it to isolate y in an equation where y appears twice? And one of those times it's differentiated. It's not very fun. But then to look at the equation I have now, how many places does y appear? Somewhere. And it is not even fully and properly differentiated. Is it a bit after all, right? But you can see that the point is, y only appears in one place now. So now you can solve for y. Then I can find the solution. Because what were we looking for? Y is x. We're looking for a function that, if you differentiate it and add the untouched function multiplied by a known function, results in another known function. That's what we are searching for. That is y. And it's easier to find now, because y appears only in one place.
So let's move on.
If I want to isolate y, I first get a bit annoyed that there's ddx there. So I think I can just get rid of that ddx. What is the opposite of differentiating with respect to x? It is to integrate with respect to x. So I just integrate on both sides of the equal sign. If I integrate here, then the differentiation disappears. They are each other's opposites. They cancel each other out, those two operations. So I am left with e raised to the power of capital F times y. What it has cost me is integrating on both sides. So I need to remember to write that I am now integrating on the right side.
I'm just switching the order of the factors.
It means nothing, but that's just how I like it best.
And remember, an integral sign is always concluded with the symbol dx. So that symbol is part of what means I am now integrating with respect to x. And when you do an integral like that, I don't know if you remember, but you need to add a constant to get all the solutions. To get all the antiderivatives, we write plus k. Do you remember that? Which is in 3 dimensions, or plus c, as we call it now, and k can be any real number. And now we're almost there, because what I was looking for was y.
So I just have to divide by this cake on each side, and then it disappears.
So I divide by e to the power of big F on both sides. But see that dividing by e to the power of f is the same as multiplying by e to the power of minus f. Because there is an algebraic rule that says this: 1 divided by a raised to n is the same as a raised to the power of minus n. So dividing by a to the power of n is exactly the same as multiplying by a to the power of negative n. Therefore, dividing by e to the power of big F is exactly the same as multiplying by e to the power of negative big F. That's how I do it when I write it now. So y stands alone now, because I have essentially divided this away. And that means that on this side, I need to multiply by e to the power of negative capital F. And then I better put a big, lovely square bracket. It doesn't have to be square. I just think it looks a bit nicer this way. And sometimes I draw it really nicely when I bother to do it like that. But it's up to you how you draw that bracket there. But here, both terms need to be inside a bracket, because there are two terms. So the integral of g should be written there.
Integral of e to the power of x with respect to x.
And then plus k.
And I don't have that.
There is a pen for the fearful.
This is called the armor formula.
And that is the solution to all differential equations that have this structure. Here is the solution. And because it looks a bit overwhelming, it has been dubbed the Panzer formula.
It ends.
Pets. Petsaphone. And it's 11 o'clock now, right? Close to 1:45. What time do we stop again? 10:02. So I can just show an example of how to use this technique. And then I recommend that you go home and practice the derivation. So that's your homework for next time. Practice this derivation. Then I will avoid giving you additional tasks. But practice the derivation. And then we will do some calculation exercises next time. But let's try to work through an example of how to use the formula.
One can, for example, the formula to figure out how quickly a cup of coffee cools down.
Or how quickly a capacitor charges. Or how quickly
The
a
capacitor is being discharged.
And if one is curious to apply it, I've recently made some videos in physics that can be found
on my YouTube channel.
where I use exactly this type of differential equation to derive the discharge and charging process of a capacitor in an electronic circuit, and it is covered in the physics curriculum. Let's try to take an example. So I erase everything on this armored guy, which is the formula shown there. Let's try to come up with a task that resembles something where you can use the formula. And what was it now? It should look like this. If it doesn't have this mathematical structure, then you simply can use the formula. It needs to be written like that for the formula to work. So let me try to come up with an example. Let's say you have a differential equation called y prime plus 2 times
You
y.
have to be equal to x.
You can probably imagine how difficult it is to solve that in your head. Can you find me a function which, when you differentiate it with respect to x, and leave it untouched and multiply by 2, should yield any value of x in x itself?
I just can't see it.
It's not bad that there are some people who can see it, but then they probably can't get curious, I think. It's probably a bit of an exaggeration. There are probably some who can see it. I just can't see it. So, because I can't see it, I have to use this wonderful formula that I once learned the proof for. And that's the thing with mathematics. It expands our abilities far beyond what we can imagine. Far, far, far beyond that. There are an incredible number of problems that can be solved with math that would be hopeless if you hadn't learned it. So what it does is enable ordinary mortal people who don't have an out-of-this-world IQ from the Pleiades of 300 to solve those problems. And all you need to do is recognize that what's written there corresponds to facts. And what is written here corresponds to GACS. This is called pattern recognition. If you cannot do that, you cannot do mathematics. But fortunately, almost everyone can. They can see that this must correspond to that, and that must correspond to that, and then it fits into place. And that's GACS, so we just start using the formula. Y equals Euler's number raised to the power of a negative primitive function of f. Okay, a negative primitive function of what? Of 2. What is the primitive function of 2? Oh, that's 2x. They are the derivatives of 2x. What does that give? So 2x is an antiderivative of 2, then multiply by a nice square bracket, and then write an integral sign. Then write the function g, which in this exercise was x, and then multiply by Euler's number raised to an antiderivative of 2 up to 2 weeks. Remember to end your integral sign with the symbol dx. So we do that. And remember to say plus k, so you get all the solutions, giving you the complete solution to the differential equation. And then one might think, oh no, I have to be able to solve that integral. And fortunately, we've nearly solved that integral in class. I know we can remember it. I solved the integral xe to the x for you. And then afterwards, I used it to solve x squared times e to the x. And then I used it to solve x cubed times e to the x. I don't know if you remember, but it's been a little while now. But to move forward, we need to solve this integral. It might be tempting to use a computer or enter it directly for the computer to solve, but if you insist on learning it by hand, which is what I'm doing, and insist you should do, especially in the first semester, to gain some hands-on experience, craft in your fingers so you know what you're doing. So we need to see if we can solve the integral x times e to the 2x. We need to tackle that separately over here, and I think time will be up once I've done that. But let's just do it. I can erase this now since I've written down the formula. So away with that. So we need to see if we can solve the integral of x times Euler's number raised to the power of 2x in respect to x. This is called partial integration, which I have reviewed for you. And I don't know if you remember, it was about finding an antiderivative of one part while keeping the other part unchanged, minus the integral of the antiderivative of one part times the derivative of the other. That was rule number 3 for integrals, and I called it partial integration. Now you need to decide which of the two functions you want to differentiate and which one you want to find an antiderivative for. And you can see that this one becomes significantly nicer when differentiated, so I'll call it g. And I can definitely find an antiderivative for that, so I'll call it f. And then I use the formula that's written over here. So let's try to dive into it. What is the primitive function of e to the power of 2x? And fortunately, it is itself. But I just need to remember to write a 1/2 in front. Why? Well, because what do you get when you differentiate e to the power of 2x? You get e to the power of 2x times 2, right? And that's a composite function. So you have to remember to multiply by the derivative of 2x, which gives 2. But the times 2 is cancelled out by the 1/2 I wrote in front, so it all adds up. So try to differentiate this. 1/2 times e to the power of 2x differentiated gives 1/2 times e to the power of 2x times 2. 2 cancels out with 1/2, so it gives e to the power of 2x. Bang, that's correct. That was an antiderivative. Multiply by the other one, unchanged, which was x. Then we write a minus, because that's what the formula tells us, and we proved it back in the agricultural era. Then we write a new integral sign, where you again write the antiderivative 1/2 e to the power of 2x. 1 differentiates g, but that gives a 1. And then we are almost there. We can't do anything more with this, so I can copy-paste after myself there. The antiderivative of 1/2 times e to the power of 2x, what is that? Well, it's 1/2 times e to the power of 2x, if you remember to multiply by 1/2 again. So that must give minus 1.
15 minutes and 2 extra.
And now I can take this. Now I've found it and plugged it into the integral spot. Then I'm finished. So the complete solution becomes e to the power of minus 2 x times parentheses 1/2.
times x times e to the power of 2x minus 1/4 e to the power of 2x plus k. And if I then multiply this with that, and that with that, and that with that, it might look a bit neater. Because e to the power of negative 2x times e to the power of positive 2x cancel out and give e to the power of 0. So when I multiply it in, from the first term, I just get 1/2 x. And from the second term, I simply get minus 1/4 for the same reason. Because 2x multiplied by negative 2x gives e raised to the 0, which is 1. And finally, I have to say plus k multiplied by e to the power of negative 2x. And here, and I can tell you, it would have been difficult to come up with that. That right there is the complete solution to the differential equation. And if this were the temperature of a cup of coffee as a function of time, then x would play the role of time, and y will represent the temperature of the coffee. So the coffee's temperature depends on time in this way if that were the problem we solved. It's not, but if it were, that would be the interpretation. And then you could just input a specific time in place of x here and there, and out would come a number, and that number would be the temperature of the coffee at that moment. And it is indeed brilliant that someone has invented a tool that can answer something as complex as what the temperature of a cup of coffee will be in 27 seconds after we've poured it. So it's not that easy. And that's what differential equations can be used for, to answer how the future looks for this measurable quantity in a little while. Yeah. This is what differential equations can be used for. So it's almost everything, can you imagine? You can simulate an entire universe with differential equations. So I usually say, if God exists, and I don't know if God exists, but if God does exist, then God can solve an insane number of differential equations in a nanosecond. And if God does not exist, then the universe can do it. So regardless, we need to learn about differential equations.
Thanks for today. See you next time.